All right, let's take a look at this lab, the rotating sky. The rotating sky student guide. And this is what we're going to fill out as we go down through. You'll see all these little blank spots. Here's a map of the celestial sphere. It's called the fisheyes view. And some other neat stuff as we come down through here. Okay. All right, so best place to start is at the beginning. So let's take a look. Background information. Work through the explanatory material on the observer, the two systems, celestial horizon, the path of stars, and bands in the sky. All of the concepts that are covered in these pages are used in the Rotating Sky Explorer that will be used or explored more fully in the lab. Okay? So, background information. Let's take a look at that background information right here. The horizon plane. The horizon coordinate system is defined with respect to an individual observer standing on the Earth. The horizon in astronomy is not quite the same as the horizon we see on Earth. It is idealized to be free from geographical effects such as mountains, valleys, or even the bending of the Earth. It is a flat plane, tangent to the Earth's surface, where the observer is standing. Consequently, an observer can only see half of the celestial sphere at any given time. And there he is. Here's half. The half we don't see, obviously, is under us on the other side of the Earth. But here we are. Here's our horizon. Notice there's no trees, no mountains, nothing like that. This is just the way that horizon will look to us. There are two dividing points or regions for the horizon coordinate system. The horizon plane is the one where the directions are given with respect to the cardinal points, north, east, south, and west. The other point is straight up, and this is called the zenith. All right, so if we move this map around, in which we can, okay, it's talking about north, east, south, and west, all right? And the zenith, if I click the label, zenith is right above your head, straight up from your head is the zenith. Take a look at it from several different angles, but right straight up is the zenith, okay? All right. Azimuth. Azimuth is the coordinate defining directions parallel to the horizon, red in the figure above. So here is my azimuth, and I'm going to show you how we get that number. Azimuth goes from 0 to 360, starting with the north at 0 and increasing towards the east. That is, east is an azimuth of 90, south is an azimuth of 180, and west is 270 degrees. Stars with the same azimuth lie on an arc from the zenith through the object down to the horizon, meeting perpendicularly, called a vertical circle, though technically it's only a half circle. So let's take a look here. We all know that a circle has 360 degrees, okay? My azimuth starts here in the north at 0. So if I take this little star here, put it right here on the horizon, move it around directly north, boom, you can see my azimuth right here. Now, I'm pretty close to north. It's not exact, but it's close, and I can move it around a little bit here and there with my mouse. We can try to get it exactly at 0, but that's going to be hard. So 0 all the way around to 360. And you can see it's almost at 360 now. If I go to the east should be, what, 90? Boom. And you can see it's 91 there. But you get the idea. 180, 270 is west, and then north again at 0 or 360. So that is my azimuth, okay? Because Earth rotates around the axis aligned with Earth's poles, the sky moves east and west, but not north and south. The observer's meridian arc from the north point on the horizon up through the zenith and down to the south point of the horizon. The meridian is the most important reference as it is a place where an object in the sky, like the star, sun, or moon, will be highest in the sky. So again, now it's talking about this. And the highest I can get is 90 degrees because my zenith is a 90-degree angle right here. Okay. Altitude is the coordinate defining direction above or below the horizontal plane. It's blue in the figure right here, blue. How high is an object in the sky? It measures the position of stars on a particular vertical scale or vertical circle. The horizon is altitude equals 0 straight up at the zenith. Its altitude 90 is straight down. Below the horizon is the nadir at an altitude of negative 90. But let's take a look at this again, and it's easier probably for me to explain this to you. So if we look at a star, or if I tell you, hey, you can see Mercury right now at, we'll just say this star right here. We're trying to look at the star. I could tell you it has an azimuth. If you want to see this star tonight, ladies and gentlemen, boys and girls, ladies and gentlemen, you need to look at an azimuth of 245.3 degrees and a declination of 23.9 degrees. No matter where you're standing, whether you're down at Clear Fork or you're up here where I am in Barberton, doesn't matter. You can look at that 245.3 and 23 declination. Here's my azimuth and my declination, and you'll be able to see that star. All right. All right, next page here, advantages and disadvantages. The horizon coordinate system has the advantage of being oriented towards the sky the observer actually sees. It has the disadvantage of being different for each observer, and the location of objects in it change over time. The celestial equatorial system has the advantage of being the same for each observer, and the location of the stars in it change very little over time. It has the disadvantage of not being naturally oriented towards the observer's sky. Because of these advantages and disadvantages, both systems are frequently used depending on the situation. It is better to use one or the other. Okay, so each one of us is going to have a different celestial horizon, celestial sphere and horizon, because we can't stand on top of each other and have the same zenith. We're all going to have the different zenith. But it's going to be close enough in our situation where we are that it's not going to matter that much. If you lived obviously in the southern hemisphere or at a different latitude on the Earth, you can see the latitude ring right here. This is the latitude. They're set at 41. If you have a different latitude, and let's just say you have a latitude of, if I can click on it here even. Well, it's not working. We need to switch it probably. Yeah. It doesn't work on, right here. Here's our little latitude line. So if I take this and I move, you see your zenith is going to change. The zenith is going to change for you as we go along here. I'm going to set this back at 41 now. Okay, so the animation to the right shows how the horizon system relates to the celestial equatorial system for the observer. Conversion between the two systems obey a few simple principles: altitude of the north celestial pole, latitude of the observer, altitude of the celestial equator, and latitude of the observer. Azimuth of north is always 0. Okay, so again, where the plus is used for the northern hemisphere and minus for the southern hemisphere. And that's just saying that if we are messing around with this and we go to the southern hemisphere, as soon as we cross the equator, we go to the southern hemisphere, notice that my latitude goes to the negative. Okay, We're at the equator, and then we go north of the equator, have positive numbers, south of the equator, negative. All right. Okay. While these principles are straightforward to employ, converting an actual celestial equatorial coordinate to a horizon coordinate is a bit more tricky. Because the sky is rotating, one needs to know both longitude and time to convert coordinates. As such, it is not covered in this introductory section. So, and again, we can switch back and forth. You can see where the observer is right here. And getting close to 41 again. I don't know why it's not letting me click in the box. There it goes, 41. That's about our latitude, 41. If you see it go around, it goes through Ohio and that. So, and we can switch to this model that we started with, okay? All right, rotation of the sky. Because Earth is rotating, the sky appears to rotate. Viewed from above the North Pole, the Earth is rotating counterclockwise. For an observer on the Earth, objects move from east to west. This is true for both northern and southern hemispheres. So just because you're in the southern hemisphere doesn't mean it moves in another direction. It's always counterclockwise. Though all objects rotate in the sky, the observer's path stars make in the sky. Though all objects rotate in the sky, the observed path of stars made in the sky depend on the observer's latitude. Some are always in the observer's sky, some of the time, and others are never observable. These different ways of classifying stars are discussed below. Okay, so stars that you see part of the night, and then you don't see them the whole time. They're called rise and set stars. During the rotation of the Earth, some stars rise from below the eastern horizon and later set below the western horizon. Appropriately enough, these stars are called rise and set stars. They are indicated by the yellow star trails in the animation to the left. The angle rise and set stars, including the sun, make with the horizon as they rise is the same for all rise and set stars from the observer. Specifically, the angle is 90 degrees, observer's latitude. They make the same angle in the west. In the northern hemisphere, the angle is tilted towards the south, and in the southern hemisphere, the angle is tilted toward the north. Circumpolar and never rise star. Circumpolar means it's a star you see all the time, like the North Star. It's always there for us, okay? And then there are stars that we never see that are in the southern hemisphere. Stars near the celestial poles, that's North Pole and the celestial North Pole, celestial South Pole. Stars near the celestial poles make small circles and may not pass the horizontal plane. If they are always above the horizon, they are called circumpolar stars. That's stars you can see all the time. If they are always below the horizon, they are never rise stars. Circumpolar stars for the northern hemisphere are never rise stars. Circumpolar stars for the northern hemisphere are never rise stars for the southern hemisphere, and vice versa. These stars are indicated by blue northern hemisphere stars and red southern hemisphere stars in the figure to the left. All right, so to see what this is talking about, let's add a few stars here. I don't know, let's try to add 10 and see what happens. 1, 2, 3, 4, 5. 1, 2, 3, 4, 7, 8, 9, 10. All right, let's animate this and let's see what happens. So as you can see, what it was talking about, here's a circumpolar star. It's in blue, okay? You can always see this star. It doesn't matter what time of the day, it's out there. You can see it. People in the southern hemisphere, if we go down here, you'll never see that star, okay? That is a circumpolar star or a never rise star for people in the south. Now, if we go down here again, When I move up, you can see here's a couple of circumpolar stars if I'm in the southern hemisphere. But if I go like this and I start to move this back, this turns red. I will never see those stars from here. Here it comes. Watch. We'll never see it. It always stays in the southern hemisphere. So that's what it's talking about. The yellow are the rise and set stars, and the blue is never set or a circumpolar star. And these red back here are never rise stars. They're always going to be only visible in the southern hemisphere. Object location in the sky. The celestial poles and the celestial equator can be used as reference points for identifying the location of other objects of interest in the sky, like the sun, moon, and visible planets. It is often instructive to crudely describe where these objects can be located in the sky for various latitudes on Earth with bands of declination. The ecliptic is the plane of the Earth's orbit around the sun. Because the Earth is tilted about 23.5 degrees to the orbital plane, the sun's declination is always between 23.5 degrees on the summer solstice and a negative 23.5 degrees on the winter solstice. Thus, one can picture a band 47 degrees wide centered on the celestial equator. The sun is always in this band. So if we come over here, we can see the sun's band right here. This is where the sun is always seen from our latitude of 41 degrees, okay? This is where the sun appears to move through the sky in the ecliptic, back and forth in the ecliptic, okay? The orbits of other objects in the solar system are described with the rotation to the ecliptic. The moon's orbit is inclined by about 5 degrees to the Earth's sun orbit plane. Thus, the moon is located in a larger region of the sky. Moon and the planet's location. There's a sun and then the moon. Notice the band's just a little bit wider. The orbital inclinations of the brighter planets are small. For example, Mars' orbital inclination is only about 2 degrees. Because orbital inclination is measured from the center of the sun and declination is measured from the center of the Earth, Mars can be as much as 6 degrees off the ecliptic. The only planet that can be very far from the ecliptic is Pluto, but it can't be observed without a good-sized telescope anyway, so thus the location band for the bright planets is very similar to that of the moon, and the two are shown as one 60-degree band in the sky band simulator. All right, now we've finished this background information, so let's take a look at part 2. Open the Rotating Sky Explorer. The Rotating Sky Explorer consists of a flat map of the Earth, celestial sphere, and a horizon diagram that are linked together. The explanations below will help you fully explore the capabilities of the simulator. Let's take a look at the simulator. Okay, so here is the Rotating Sky Explorer, and you can see these two maps side by side. Okay, instead of that one where we were hitting switch and back and forth, here they are, they're together. All right, side by side here. Let's see what it tells us to do next. You may click and drag either the celestial sphere or the horizontal diagram to change your perspective. A flat map of the Earth is found in the lower left, which allows one to control the location of the observer on the Earth. You may either drag the map cursor to specify a location, type in values for the latitude and longitude directly, or use the arrow keys to make adjustments in 5-degree increments. You should practice dragging the observer to a few locations: the North Pole, intersection of the Prime Meridian and Tropic of Capricorn, etc. All right, well, let's take a look at that. Oh, right here, we can see. We can drag all over. And notice as I'm moving it, it moves here on the Earth, and it moves here also. So if we want to go to, say, Ohio, right about there, huh? Maybe a little farther north, but there we go. Okay, so we can move it around there, or we can moving around with this right here. There's some 51. How about 90? And we know that's the North Pole. See there, North Pole. We could do a 90 south and go to the South Pole. All right. So we can move the observer around right down here. Put them back at 41. Boom. There we go. Note how the Earth map, celestial sphere, and horizon diagram are linked together. Grab a map cursor and slowly drag it back and forth, vertically changing the observer's latitude. Note how the observer's location is reflected on the Earth at the center of the celestial sphere. And we're going to kind of skip through this. All right. I've done this before. I know how it works. If you want to read through it, you can. But let's take a look at what needs to be done now here. Okay. All right. Here it is. Number 3, horizon coordinates. Horizon coordinates. Question 1. Complete the following table involving the horizon coordinate system. You should predict the answers and then use the simulator to check them. Remember that you can measure coordinates by dragging an active star to that location. All right, so let's take a look. All right, so the west point of the horizon latitude is any. What would the azimuth be? Well, let's take a look here. Here's the west point of the sky, or the west point right here. Our zenith, of course, is up here. It says it doesn't matter what our latitude is, so we're just going to leave that there. Now what we're going to do is we're going to add a star randomly, and here's our star. That way we can take this star and put it wherever it wants us to put it. And we know that the azimuth in the west should be 270. Boom. Our altitude is 0. So there you go. What is... what's that question again? Let's look at the question. What is the latitude any? What's our azimuth? Our azimuth is 270 degrees. West point of the horizon, 270 degrees, and the altitude is 0. So write those in. Type those into your boxes. 270 and 0. 270 and 0. Where's the zenith? It doesn't matter what the azimuth is. It doesn't matter what the latitude is. Just the zenith. Let's take a look at our zenith. Okay, and we know, we've talked before, the zenith is straight up, that point right up in the top. So let's take this star and let's put it right there. And we should know that this would be 90 degrees. Okay, it said, I believe it doesn't matter what the azimuth is. Azimuth, any altitude is 90 degrees. It's straight up. It makes and how am I getting 90 degrees? If you guys don't know, I'll go back here again. Right here. Let's go to the side. It'll be easier. Here's a 90 degree angle from the north straight up. 90 degrees. So my declination here is 90 degrees. Said it didn't matter where the azimuth was. So we're going to put 90 degrees here. Okay, so west point, our description is a north celestial sphere, latitude 30 degrees north, or the north celestial pole. North celestial pole at 30 degrees north. What is the azimuth and the altitude? Well, let's figure that out. If I can get this, there we go. All right, so here's my north celestial pole. And we can show by dragging this to the north celestial pole, boom, right there. Oh, we have to change the observer. What did they say it was? I'm sorry. I think 30 degrees. We have to be north, 30 degrees north. Boom, there. There's our north celestial pole right there, right above the north. So let's take this star we made that's at the south celestial pole, and let's move it over here to the north celestial pole. It looks pretty good right there. isn't it? Close enough. Close enough. And I here have 0.2 degrees. It should be actually 0 or 360, but we're close enough. 0.2 degrees on my azimuth, 0.2 degrees on my azimuth, and my declination is 29.4 degrees. We'll come back here. I think we had 0.2 for our azimuth, our 0.2, and 29.4. So our azimuth is 0.2 and our declination is 29.4. So you'd put 0.2 and 29.4. The North Celestial Pole, if our latitude is 71 degrees north. So what we're doing here is we're moving the person around on the planet. Okay, we're moving them around. If you notice here, we were at, watch the little white dot. We were at 41. Okay, then we went to 30. Now we're going to move ourselves up a little more. What does it say? 71. So let's go to it. 71 degrees. That's going to move us towards the North Pole. And watch the North Pole over here jump. We have that star there. So all we have to do is change our latitude. Boom. And look at that. Now, okay. Our azimuth is at a 0.6. And our North Pole now is 70.4 degrees. 70.4. So 0.6 and 70.4. 0.6. 70.4. 0.6 and 70.4. South Celestial Pole at a latitude of 52 degrees south. So let's change this to 52 degrees south. Now look where we're at. We're way down here. Now we're looking at the South Celestial Pole. Okay. So we know the azimuth is already going to be what? Anybody remember? 180. And our altitude, we're just going to make this a small positive. I don't know. Let's go 50 and see what happens. Boom. Holy smokes, there it is. Guessed that pretty good. So for the southern hemisphere, the southern celestial pole, looks pretty good right there. We're at 180 or 179.8 and 50. Looks like 51.7. It's close enough again. So 179 and 51.7 there. The Tropic of Capricorn. Tropic of Capricorn. I'm going to tell you on this, I'm not sure if we have the Tropic of Capricorn. I believe that is going to be over here, 23.5 degrees. And how do I know what the Tropic of Capricorn is? It is the lowest part, or it's the farthest part south the sun travels in the ecliptic. So it's 23.5 degrees. 23.5 degrees. Because remember, the ecliptic is off by 23.5 degrees. So, or the tilt of the Earth. All right, what did it tell us now? Tropic of Capricorn, azimuth, and the altitude of the North Celestial Pole. Click on that star. 23.2 degrees and 179.9. So 179.9 is our azimuth. 23.2 degrees. It's going to be close enough. And those two numbers will go right in here. You should know azimuth and altitude by now. Okay. Intersection of the celestial equator and the meridian at 40 degrees north. Let's check that now. 40 degrees north. So we got to change this back to 40 degrees north. And then we can, should be able to click on these right here. This is what we're looking for. Okay, here's a celestial equator and the meridian. So let's take a star. Let me look at this one more time, this question. Intersection 40 degrees north. So let me find my star again. I think we could either take this right here, or we can go over here and take it from the other side. So, all right, I knew there was a button here. I did find it. That's why I paused this for a minute. It's right here, show the labels, and we're at 40 degrees. Let me just double check. Latitude 40 degrees. Okay, all right, so. Right here is the spot we're talking about. So let's move our star over to that spot. Excuse me. Right here. Okay. Oh, I'm sorry. Let's see. Yeah. Okay, so here's our meridian line coming right through here. And here is the celestial equator. So what we want to do is we want to take this star and put it right where these two cross, right here. That's close enough, right? My azimuth is 181.4 and 49.9 is my declination. So we'll just jot those down right here. And again, the reason I'm doing this video, you can back it up, you can fast forward, you can do whatever you need to get these numbers in here, okay? And then intersection of the celestial equator and the meridian, if my azimuth is 0 and my altitude is 35, what's the latitude going to be? So let's check that out. If we can get this to pop up, there we go. So what we're going to do here, our azimuth is 0 degrees. And our declination is 35 degrees. Okay. The question is the intersection of the south meridian. Intersection of the south meridian. And I'm going to make this easy for us. We have to get it to where that star is over here. And what we have to do, saving us time here, right here, 55 degrees south. 55 degrees south is where it has to be for that star. Boom. Boom. To match up. 35 degrees right there. Okay, here's the meridian and the celestial equator. All right, just saving time. So the answer to this one is 55 degrees. We're going to stop right here. This will be our first section of the lab. And again, what I will do is I'm going to let you guys work through this, and then I will go over these answers again in class, okay, at some point. So I hope you're getting something out of this lab. It's weird to work through them like this because I've always done this in class. So we'll see how this works, okay? Everybody have a great day.